forgotten tea.
Yeah, that'd be great.
Good to go.
All right.
All right, we are resuming our session. We have 20 people. People are mostly back. I'm going to go.
Okay, well, Fari came in to test the AV. I'm sorry, Fari, we're kicking you out. The session's starting now.
We've got 30. Let's run over 30 seconds. Fari, throw up your slides real fast.
Okay.
Okay, slides fast. No, I don't need that. That's okay. No, we did that yesterday. Don't
okay, just Fari, don't go into any other session than this one, okay? Otherwise, we can't invite you on stage.
Okay.
All right, I'm throwing Fari off stage, and we'll get started. Okay, it's time. We're 1 minute over. Welcome back, everyone. Our next speaker is Ian, who is going to, I always love a talk that has music in it. So we're going to get how to do music in Scheme, getting peanut butter on your chocolate.
Sounds good. Ian, I can take it away. Okay,
yes,
great.
Please do.
Okay, hi everybody. My name is Ian Duncan. I am a software architecture consultant and a music technology master's student here in Victoria, BC. And I am the author of Scheme for Macs. And that is an open source project that extends the Macs MSP computer music programming environment, enabling you to run Scheme code in your Macs patches. Now, the paper goes into some detail on how this is implemented, especially the interesting feature of how it schedules future events. But I'm pretty confident that if you're at this conference, the computer science part of that paper is going to be very easy to understand, whereas it's much more likely that you might not know anything about Macs or the world of computer music programming. So for the presentation, we're going to focus on that. And I'm going to show you what Macs looks like and why you might want to use Scheme in Macs. So we'll start screen share here. Okay, sorry, screen share. Okay, so hopefully that's, is that showing now, William? We're all good?
You're good, yep.
Okay,
perfect.
Great. Okay, so Macs is a visual programming environment. It's a data flow environment where you connect boxes with virtual wires. And so this is an empty Macs patch here, and I'll just drum up a very simple Macs patch for you. Just a second here. I'm not sure why it's demo day problems already here. Okay. We're going to put in a number box. Retype that properly. Okay, and I'll just make this a little bigger so everyone can see it. And then we're going to add in a plus operator. That's a function that adds 100. And we'll put in another number box. And so we make our program go by connecting wires from the outlets to the inlets. And now we can see we're able to update the bottom. So it's a data flow, kind of like a spreadsheet. Now, the killer feature about Macs is really that it's extendable. So Macs was written in the late 1980s by Miller Puckett at IRCAM. And it now exists in a couple of major forms. There's the commercial Macs MSP product from Cycling 74, and Miller also rewrote it as an open source product called Pure Data. Scheme for Macs exists for both of these, but we'll be focusing on the Macs one today. And so the really interesting feature about Macs is that you as a user can write new objects in C. And so you can write a plugin, they call it an external, and your object has some factory functions that create the object when you drag it onto a canvas. So really when we're programming with an instantiation of an object. And then you add bound methods and they run in response to messages coming in. Objects communicate with each other by sending messages that can be numbers or symbols or lists of numbers and symbols. And then your methods can do things like calculate values and send them out the outlets, update their visual state as these number boxes did, update some internal state, or perhaps have side effects on the broader Macs environment, such as writing to data structures or changing the tempo. So for example, we can add another number box here. If we put it in the right-hand inlet, we're now just updating the internal state of our adder object, and we won't see anything happen until we ask the adder to run its calculations. But now it's adding 11. So that's sort of your simplest possible Macs patch. Now let's take a look at a more typical one for making computer music. Okay, so this is a simple synthesizer patch. We've got an input widget here that came with Macs of a little keyboard. We've got a couple of dials. I've hooked that up to velocity and duration. These go into an object called MakeNote. And MakeNote is a fairly complex object. It knows how to make a MIDI note. It also knows how to send the message that has to come later to turn off a synthesizer. That's how MIDI works. You turn on a note, and later you have to tell it that your finger has released the key. These go out through some parsing objects. We don't have to worry too much about those, and into this container that holds a commercial synthesizer plugin. So now I can click on here, and hopefully everybody's hearing the fact that the synthesizer is playing.
We can.
Great. And so this gives you an idea of what a more realistic Macs patch might look like. It's still quite simple. And probably you also get a sense of both the advantages and disadvantages just from looking at this. It's a great way for composers and performers and musicians to quickly lash up some kind of a program that they want to interact with. It's great for making programs that you might use only for one piece. On the other hand, you can also imagine that this paradigm would get really cumbersome really quickly for things that are quite complex, for formulas, for handling any really complicated flow control, that kind of thing. And so within Macs, of course, you have the option of doing that in C in an external. Some people do that, but the C SDK is very low level. It's not the kind of thing most people would want to do for the purpose of a single piece. You do also have the option of scripting Macs in a text programming language. And the major one of these that comes with Macs is the JavaScript object. And so it's an object just like the other objects, but it in turn holds an interpreter, and you can run JavaScript code and interact with your Macs patch. So Scheme for Macs is essentially very similar to the JavaScript object, but instead of running JavaScript, it runs S7 Scheme, which is a scheme interpreter made by Bill Shodstad at the Computer Music Center at Stanford. It's used in quite a number of computer music projects. And the reason that's important is because really Scheme, Lisp in general, but I think Scheme particularly, just make a lot more sense for expressing musical constructs. Musicians speak and think in high-level abstractions, and those abstractions are often functional. So we will say things like, that F7 chord is the 5 of 2. That's really a chain of functions. You know, what does an F7 mean? It's a set of calculations over a root note. What does a 5 chord mean? Same idea. What's a 5 of 2? And so expressing music thoughts in Scheme and in Lisp is very natural, both from the support for higher order functions and also because it's so easy to move back and forth from the symbolic domain to functions. So that's kind of the purpose of Scheme for Macs. And it also has a couple of tricks up its sleeve that were not practical with JavaScript. So let's take a look at some Scheme for Macs patches. Okay, so here's the very simplest possible Scheme for Macs patch. Really, we're doing the same thing. We've hooked it up to the same MIDI output objects. And you can see I have a couple of blocks of code at the top. This toSymbol and prepend eval string is basically just some housekeeping. This is what they output at the bottom. And that message goes into the Scheme for Macs object. It runs the interpreter, and then, as requested, is going to run its out function that says outlet 0, please send the list 6064, and that should turn on our note. And of course, as we mentioned, I've got to lift up my finger. Now the note's off. So there's our simplest possible use of Scheme for Macs. Now let's take a look at a more complicated one. Okay, here we have something pretty similar, but this time we've replaced one of the numbers with the variable note. And one of the tricks that Scheme for Macs has that is not in things like the JavaScript object is that the nature of Scheme syntax works really, really well for going back and forth between Macs messages and code. And so one of the things it does is if it receives a message that is not otherwise bound to a specific handler, it interprets it as being a message that should be surrounded by parentheses. And so what I've got over here is the message define note $1. The $1 comes from Macs. It's a variable interpolation facility. And so you can see when I move the number, it becomes this message down here. That message goes into Scheme for Macs. It's interpreted as a function call. And we have a really, really easy way to make input widgets into our program. Really, it requires one message box and then into the interpreter. So I can now change which note we're hearing. change it again. So we're running code a couple of ways into Scheme for Macs. Okay, let's take a look at a more complicated one. Now the next thing is Macs has a lot of facilities for interacting with the broader computer world, including network listening. And so what I'm able to do is, oh, have a little error meet sign in the way here. I'm going to work in an editor. We have a very simple program to play a note. That file is getting loaded as the default file. But in addition, I've written a little Vim extension that allows me to send code over the network directly into the interpreter. So we're going to do that here. I've defined the play note function, and I'm going to play a note. Sure. A bit long. Oh, I've got to just make that stop flickering. Great. Okay, now let's take a look at the play note function. As I mentioned before, one of the challenges is that with MIDI, you have to send out that note off later. And that requires us having some ability to delay things. And as you can probably imagine, looking at Max patches, doing that in a visual programming environment where you're programming with instantiations as opposed to classes can get very cumbersome very quickly. However, the Max SDK does have a facility for firing an arbitrary one-argument function at a C level very precisely. And so the Scheme for Macs system piggybacks on that to make it really easy for us to simply request a no-argument function at a specific time. And I've done that using the function delay. So in order to send out my MIDI off event, all I need to do is schedule a Lambda function with the velocity 0. And so that's why play note doesn't hang. You might have noticed play note, I can now actually think more the way a musician thinks. It's an eighth note. I put in the eighth note duration. I don't have to remember to go and turn something off an eighth note later. So that's the facility that I look at in some depth in the paper, the implementation of that delay. But let's take a look now at how you might use it more interestingly. So I'm going to load up the next file. And one of the other interesting features of Scheme for Macs is I can add new files to the session without wiping the interpreter. That's something that's not possible in the JavaScript object and is actually very useful when you're building interactive programs. Okay, so let's look at number 2. We're going to play the world's simplest sequencer in 25 lines of code. Okay. So we've got our play note function. That hasn't changed. We've got some variables we're going to use. And then we have run step. This is executing one step of the sequencer. It does some calculations in a let. So it has a list of pitches in the pentatonic scale. It has a randomizer. So this is an algorithmic sequencer. It picks a next note from a pentatonic transposition of the existing note. It also picks a random velocity from 60 to 120, plays a note using those settings. And then the nifty part is it checks to see whether it's supposed to be playing based on that global variable. And if so, reschedules itself. So functions are able to reschedule themselves, and that will just keep going until we tell it to stop. So let's fire it up. There we go. It's just randomly wandering around the pentatonic scale until we tell it otherwise. Okay, now I'm going to trip the power cable, and we stop. So you can see it's pretty easy for us to send code directly into the engine while it runs. And this has a lot of value for several different kinds of people working in Macs. There are people doing algorithmic composition. This was a little mini example of that, in that there's an algorithm running to determine the notes. It has value for people writing sequencers, performing live electronic music. So people who make drum machines or synthesizers that run on stage and they improvise the music. And also it has value for the live coding scene. These are people who perform the actual coding on stage, much as I am doing now. If you imagine the piece was more interesting, perhaps that would be a live coding performance. The code is going in while the music plays. So the last thing I want to show you before taking questions is a more complicated version that combines some of the things we've talked about now, and especially one of the features that I explore in the paper. And that feature is that one of the unique things about the way we're handling delayed events in Scheme is that by doing it as closures, we're able to specify we would like to use a setting from an input widget, either as it is now or as it is going to be when the scheduled event comes up. So let's take a look at that. I just need to break a cable so that we don't have the network input going to 2 patches. And I need to attach it over here. Okay, so let's pull up that synthesizer. So this one is a little more complicated. It's not a lot longer though, actually. And what we've got going on is a couple of input variables that we're going to send into the sequencer. One of them is our set tonic, and one of them is our set base velocity. But if we look over at the code, we've got some interesting stuff happening. When we schedule a run step, instead of scheduling the function run step and having the closure as a function object sitting on the scheduler, we're going to schedule a Lambda event that evals this call here. And by doing so, we're saying each time we start this off, use the value from base note as you're going to get it evaluated at that time. On the other hand, we also have velocity, and it's being read from a variable. It's going to get the value of velocity as it is when the time expires, when it's up. So what that means is if we start this sequencer off, we can be changing this dial, we'll hear it right away. We can be changing this dial, we won't hear it until we ask to start the scheduling process again, to kick off that process. So let's try that out. And then I've also hooked up some start and stop functions here. They're pretty straightforward. The restart just interrupts that scheduling chain by canceling that delay and restarts it again so that we grab a new base note. Okay. Let's turn that up a bit. Okay, so it's doing its thing. And if I move the velocity knob, we can hear that effect happening right away. Right, so we're grabbing that as it is at the time the event expires. If I change the key, nothing's happening right now until I hit restart, when it gets captured and kicks off a new evaluation chain. I'll pick a more distant key. Maybe we'll hear that better. Okay, so that's one neat feature. And the second neat feature I want to demonstrate is the ability for us to actually redefine run step on the fly. Again, because we're using an evaluation of the symbol, if run step changes, the scheduling chain is going to catch the new run step right away because it's being rewritten at the global scope. So I'm going to start this off again. And I'm going to change my algorithm on stage, so to speak. So we're live coding. And I'm going to say, flip a coin on every step. And half the time, go change your duration. So I'll just pipe in the new version of run step while it's going. Now we have changing durations as well as changing pitches. And if I decided I didn't like that as much, I could just redefine it again. You're probably hearing a couple of glitches. I should mention those don't happen when you're not also broadcasting on AirMeet. That's an artifact of the computer trying to do too many things over the audio card. The timing is solid when you're just running this in Max. And so you can imagine this is great tool for people wanting to build sequencers on the fly. The fact that you can redefine the functions as it's playing, I've found hugely helpful in building applications. I've done things like build ear training applications and larger scale sequencing environments for making electronic music. And it's great not to have to recompile or even stop the piece. And it also brings the facility of live coding to Max MSP. And part of the purpose of doing this was that I wanted to make sure that you could work this way, you could work in Scheme, but still capitalize on everything that's available already in the Max environment, which is a huge, huge library. There are thousands of externals for doing computer music. So that is the overview of Scheme for Max and what it does. And if you read the paper, you can read the details on exactly how the scheduling was implemented. It's pretty straightforward. I mean, the closures get a unique handle. They go into a hash table. In C, the clock gets a data structure that has that handle. When the time expires, it calls back into Scheme, fetches the closure out of the hash table, executes the function, and discards the handle. That's the implementation in 15 seconds. Okay, I'm happy to take any questions.
Can you play Freebird?
Okay, or Stairway to Heaven.
Yeah.
Okay,
no Stairway.
Yeah.
We actually do have an audience question already.
A real question.
We have a real question.
Okay. Yeah, let me read it out loud so
sure.
that people can hear it. In your ICFP-3 example, I see lambda, eval, run step, base note at the end, which seems to be a poor man's closure. Are closures implemented in S7?
So yes, I mean, the reason I did it that way was I was trying to kill two birds with one stone. I wanted the real purpose of the eval list run step was to be able to pick up the new evaluation of run step whenever it changed. But you can do, standard Scheme closures in S7. S7 is basically R5 RS with a bunch of extras that Bill Shodstedt has put in. It has a lot of Common Lisp features. Bill is the author of Common Lisp Music, so it's a bit of a hybrid in a sense. It's kind of similar to Clojure that way. But aside from no syntax case, no syntax rules, you do get pretty much standard R5 RS Scheme with Common Lisp macros.
Okay, it's just that I would have expected that if you access a global variable and it has been modified, then you would get the new value, even if you use a closure.
Yeah, so I mean, it depends what you're. Again, that I was trying to optimize for cramming things into 20 minutes. Maybe that wasn't the best example then, but yes. So if you want to, you can build a closure in your Lambda and capture what you want captured in a let, and then read a global for the things you don't want captured. In retrospect, given your question, maybe trying to roll those two into one example wasn't the best idea.
Okay.
But yes, you can do that. So that's typically what I do. And a lot of the code is, I'll have something I want to capture goes into the let, something I want to just use globally just reads the global value.
Okay, thanks.
Any other questions? Okay, so we have, is this available? Oh, sorry, you're supposed to read the questions, aren't you, William?
Yes. Is this available on Linux? Sorry, William, go ahead.
Is this available on Linux?
Okay, so yeah, it's available for Pure Data on Linux. So Max doesn't run on Linux, Pure Data does. I have ported it to Pure Data. The Pure Data release is younger, so at the moment you still have to build from source. And there are some features. Pure Data is more minimal than Max, so there are some SDK features that aren't on the Pure Data version. But everything I displayed today, you could absolutely do on the Linux version.
And do you have
examples? Yeah. So if you look on YouTube, there's a channel called Music with Lisp, which is where I put up the videos. And so I have an example of the sequencing tools driving a Eurorack modular synthesizer for an algorithmic composition etude that I did last semester for composition class.
Great.
I just invited Marc-André on stage, so perhaps he has.
Yeah, there's another question we missed too from Francois René.
Well, let's make sure that Marc-André is done.
Sorry, I just wanted to know if you have some YouTube examples of music you created with this or something.
Yeah, so they're on the channel called Music with Lisp.
Oh, music with a, sorry.
Yeah, no worries.
Thank you.
All right, let me get, go ahead.
Okay, you want to bring up Fare?
Yes, I will invite Fare. Let me get Mark Andre off stage. Let's see.
Are we done questions, or am I answering?
We have a question from Fare.
Oh, okay.
Who I'm now inviting to stage. All right, so how does your approach compare to extempore?
So extempore is, I mean, it pretty in the same ballpark. And as a matter of fact, they both originated from using tiny scheme. But in extempore, they kind of rewrote their own language in order to do more DSP-oriented calculations. I'm staying away from that and focusing on musical event calculations. So the garbage collector isn't really a problem for my context, because as long as I'm running with about 5 milliseconds of latency, which is pretty standard for an audio environment with any synthesis going on, the GC finishes its job in time, and it's really a non-issue. I know the extempore fellows wanted to also be able to generate audio with the interpreter, and so that's why they created something that has typing in there to spare load on the GC. So I know that's one of the differences. The main difference between this one, and I see there's another upcoming question, how does it compare to overtone, which is another example, and I do talk about these in the paper a bit, the differences. The main one is that this is running in max, it's running in pure data. So one of the motivations for doing this was that the existing options, including overtone, extempore, common Lisp music, slippery chicken, there's a bunch of them, they all kind of have to be the boss. They're the main thing you work with, and then they pipe their input out elsewhere. So you might send messages out to CSound, you might send them out by MIDI, but the system you're working in is that Lisp system, whether it's extempore or overtone. Overtone pipes to Super Collider. In my case, by embedding it in a max or a PD object, I am driving off their own native scheduler, and it makes it a lot more practical to interact with other tools that you might want to use from the broader Max community. So that's kind of the big purpose, is to put it into an environment that means it's less of an all or nothing equation. You can incrementally use Scheme for Max and do bits of your computer music in it without having to kind of go whole hog onto driving everything from Lisp.
Any follow-up, Fare?
Hi, sorry. Yes?
Any follow-up? Are we good?
I'm fine with the questions.
All right. Let me throw him off stage and mark the question is answered. Let's see. Mark is answered. Do we have any further questions? Wow, perfect timing. We've got like 2 minutes. Anything else? All right. Well, thank you for an interesting demo and presentation.
Yes, thank you.
All right.
And we'll
thank you, everybody.
Glad
you enjoyed it.
Thank you for being
being
brave, trying out so many pieces of technology simultaneously in the dark.
I can admit I was holding my breath.
Me too. Okay, great. Thanks very much, everybody, and please come look me up.
All right.
Thank you.
Will, do you want to queue up the video?